All right. Yeah, that Yaddick and Pilch is it's an important paper. Like that is a very carefully done paper, and basically their ideas for superanalysis are very, very good. It's a very careful paper, and essentially, if we had paid more attention to that paper early on in my graduate work, it would have improved my thesis by quite a bit. I think the central thing in that paper is the idea that, all right, well, okay, so like one of the things we're going to learn in complex analysis that's kind of shocking, really. Oh man, my eraser shirt it needs help. Okay, so like in real analysis, you have functions which are once differentiable, right? But not twice differentiable. You know? For example, like f of x equals to x absolute value of x is a pretty standard example. That function is everywhere continuous. You can envision it as the parabola x squared and the parabola minus x squared glued together at the origin. So it kind of resembles a cubic, but of course the derivative of this is actually twice the absolute value function, which, okay, that's fine. So it's actually continuously differentiable because the f dx is just twice the absolute value function. But when you take the second derivative, you get the derivative of twice the absolute value function, which of course does not exist at 0. So it's a function which is once continuously differentiable, but not twice. And if you want to take the x and trade it for an x squared, that's twice differentiable, but not thrice. Take that x, replace it with an n, you've got something that's n times differentiable, but not n plus 1 differentiable. So these examples were first appreciated in the mid to late 19th century. That's when mathematicians really started to understand some of the more subtle points of function theory. And like the piano axioms, I think that was his example. And it leads to some really nefarious things. Like in differential equations, you can look at the Wronskian. The Wronskian is if you take the function and you make a matrix of the function and its derivatives, the second derivatives, all the way out to its, n minus 1th derivatives. That gives you an n by n matrix. Well, if the determinant of that matrix is non-zero, that implies that those n functions that you're looking at are linearly independent. And so you're tempted to say, so if the Wronskian is 0, it must mean that they're linearly dependent. But that's not true. Because there's quantifiers involved. So like it's not just a matter of switching equals 0 to not equal to 0, vice versa, because there's also for all there exists kind of stuff going on when you sort through it carefully. And so you have the situation like, for example, this set, right? If you calculate the Wronskian of this thing, if I call this, say, y1 and y2 as functions, if I calculate the Wronskian of y1, y2 at x, it's the determinant of y1, y2, y1 prime, y2 prime And that works out to 0. But those functions are not linearly dependent. Because when we talk about linear independence of functions, we have to talk about linear independence with respect to a domain. Like anybody talks about linear independence of functions, they have to be talking about with respect to a common domain. Otherwise, it's a meaningless discussion. And the thing is, with these two guys, you have, for x greater than 0, right, you've got y1 minus y2 equal to 0. But for x less than 0, you've got y1 plus y2 equals to 0. So they are linearly dependent for positive. They're linearly dependent for negative, but for different reasons. And as such, they're not linearly dependent. Because to be linearly dependent on the reals altogether, which is the domain of these functions, I'm assuming, would require for one to be, it requires them to be a linear, one of them to be a multiple of the other in a uniform sense for all reals. So, but because they're linearly dependent on the positives and the negatives, you have the Wronskian is identically 0, even though these are linearly independent functions. So you see this is what people are up against trying to unravel as they're thinking about like linear independence of functions in the 19th century. And this still confounds research mathematicians, some of them, if they haven't thought about it. Like it gets people. But the cool thing is, in the context of a solution set for a differential equation, there's something called Abel's formula, or Abel's formula, which writes the Wronskian as the exponential of the integral of a particular pair of coefficients of the functions which define the differential equation. So if you have an nth order linear differential equation, Abel's formula gives you the Wronskian is equal to the exponential of something, which means that if the exponential is 0 one place, it's 0. If the Wronskian is 0 one place, it's 0 everywhere. But more than that, it turns out from the theory there that in the context of solution sets, if you're talking about the solution set to a differential equation, the Wronskian being 0 at even one point implies linear dependence of the solutions. And so like this stuff, the Wronskian works in the context of solution sets, just like you'd like naively, but in the broader context of like judging linear independence of functions, you can't just use the Wronskian to detect linear dependence. I mean, it probably means something. It means there's some kind of linear dependence, but it may not be what you need to get linear dependence on the full domain you're looking at, like because of this issue. This is at least one issue. I'm not saying that's the only issue. I don't know. I mean, for sure. There are much uglier examples of things which are continuous but not differentiable. I mean, there's functions which are, like this one is, you know, it just fails to be differentiable at one point. There are other functions which are everywhere continuous but nowhere differentiable. Maybe you looked at those in real analysis.
We didn't get to the differentiability.
Oh, okay. Ah, okay, well, it's all good. So what was I? I was talking about this. Oh yes, so this does not happen in complex analysis. In complex analysis, get this, if you have a function defined from like the complexes to the complex, so a complex function of a complex variable, and if f prime of z exists for, let's say, z in some domain, then the nth derivative in the complex sense exists for z in that domain. The domain is an open connected set. Well, yeah, that's right, open connected set. So there are no once complex differentiable functions. There are only, in some sense, complex smooth functions, like every complex function you can take infinitely many derivatives of. So when we started studying superanalysis, we were thinking like this. We were thinking you could have, we didn't fully understand or appreciate that it is much more like complex analysis in some regard than it is like reals. So in a nutshell, the reason this happens is that the differential at a point, when it acts on H, it's defined by, well, if you have H1 times H2, you get like, now here we're talking about complex multiplication. Right? Like that's the property that lies at the heart of why this happens. It's really that. Now it takes me a month of complex analysis to prove that, probably. There's some really delicate arguments that go to proving that, but it's true. And here's the thing, is like when you talk about a function from, you know, let's say KPQ to lambda, right? And I think down here I need to assume, this is what I'm not sure, this is what I'm rusty on, okay? I assume F is smooth in the Banach sense. So remember, we talked about KPQ as a Banach space, meaning it's an infinite dimensional vector space over the complex numbers, or with respect to that norm defined by adding up the Grassmann components of the variable, the moduli of those. It's a complete space, and so it's a complete norm linear space, and it takes Banach space, so we can define derivatives in terms of the Fauché differentiable. So it's smooth in the sense of having Fauché derivatives which exist in the category of the Banach space. Well, this is the thing, is that it, you know, again, so here it's something like, you know, let's say x comma theta, and, you know, there's a constant over here. I could put it either side. I mean, this is equal to but here C is an element of it's a commuting supernumber. Now, if you read Yaddick and Pilch, they say this in a different way. But in here, they'll talk about it eventually. First of all, they do all the supervector space stuff we're talking about at a slightly higher level. That's like you won't find Grassmann generators in here. They just do things with respect to like a arbitrary like the Q is the supernumbers, but they don't get into the substructure of the supernumbers as far as I can remember. Okay. Which is actually really useful, because a lot of different people had a lot of different ways of building supernumbers. So like what they prove is true for all supernumbers, and trying to find their definition. Let's see here. So here's their definition of supersmooth functions. It's let's see here. Definition, let Q be a BG algebra so Banach-Grassmann algebra, and let U be an open subset of QMN, a super smooth function on U is a smooth map such that dfx is an element of this. Now this right here is notation for what I've called left linear maps, which is so the differential is required not only to be linear but also Q0 linear. Q0 linear is Q0 is his commuting supernumbers. And so that actually implies that the second superderivative exists, and the third superderivative exists, and the fourth, just like complex analysis. So, because, you know, saying that there's this kind of structure for the differential is an incredibly strong condition, likewise here, and it has implications for higher derivatives as well. Admittedly, if you really stop and ask yourself the question, how do you define a higher derivative in a, you know, n-dimensional context, you'll quickly realize that you haven't worked that out in any of your coursework. And that's the parts of my thesis in this book which look most unfamiliar, is the higher differentials. There's sort of iterated differentials, like the differential of the differential of the differential. It ends up needing to be interpreted as like a multilinear map on the Cartesian product of like the tangent space with itself a bunch of times. And but you can get around that, I think, if you fully embrace this lambda 0 idea. And then, because then basically, since the derivative of the derivative makes sense, it means then that the second derivative can also be looked at as the derivative of the first derivative. And so like some of the more obtuse, unfamiliar aspects of higher analysis that are in the book right now can be supplanted if you fully go down this path, like Yaddick and Pilch. I don't think Yaddick and Pilch have, like if we look through here, I don't believe they suffer the same fate as my thesis did. Well, okay, well they do talk about it here. I guess you have to talk. I mean, if you're going to talk about iterated derivatives, I guess you do need to talk about that. But how do you like multiple partials? What do you talk about? What do you mean by iterated partial derivatives? What are you actually differentiating? Is the question. And I guess we should talk more about that some other day. But what was I going to talk about? So I'm trying to get at is, you asked me about Yaddick and Pilch as we started this all. So it's a very good paper, and like, because the definition that we use for superdifferential to start with was the one from Alice Rogers, like I wrote down for you already in here, which was just that the differential has a formula that's a linear combination of like what you identify later as even partials and odd partials with respect to the superspace, right? But you're still down in the weeds with the Fauché quotient, whereas they're already like taking advantage of the Banach space stuff a little bit more. Like, well, the Banach theory gives us a Fauché differential, which we can work with, and so we can characterize the superdifferentiability by just being, let's say, lambda 0 linearity of the differential, which is a somewhat more invariant way of categorizing Alice Rogers' formula. And it's a better way. So in a nutshell, that paper is an important paper, and it's a clean and beautiful paper, which, all right, so let's go on. Let me double check on my camera. Make sure I actually turned it on. I don't remember. I did turn it on 20 minutes ago. Hey, that's not too bad. Yeah, my brother is not just a good mathematician, but a very careful mathematician, and also like his PhD thesis is essentially an infinite dimensional linear algebra. But I had to argue with him to get him to see what the Wronskian issue was, because it's just so ingrained. The idea of, the Wronskian being 0 must mean linear dependence of the functions. Now, it didn't take, once I showed him this example and pointed out to him what it was going on, he quickly overcame it. But I have seen people with tens of thousands of reputation on like the Math Stack Exchange arguing the wrong idea. It's a very seductive thing. Like this Wronskian business is tricky. And a lot of it's that the linear independence of functions is tied with their domains. Like you have to, when you talk about a set of functions being linearly independent, you're talking about, you have to think about like the linear combination equal to 0 at a variable for all values of that variable in the domain. That's the condition that you have to work with, that equal to 0. So you have to, have that holding for all points in the domain. And anyway, I digress. Okay, so what is a supervector space? Excuse me, a supervector space. No, we're past that. What is a supermanifold? So let's see here. So let me talk briefly and just write a few things. Let me talk mostly and just write a few things, all right? So it is a set with a topology, right? So I'm on page 91. So he first of all, he defines what he means by topology, which should be no surprise to you. It's a collection of subsets that includes the whole set, the empty set. If you have two sets in the topology, the intersection is also in the topology. And if you have an arbitrary family of sets in the topology, then the union is in the topology, right? So closed under finite intersections and arbitrary unions. And of course, you can get finite intersections from induction on two, but I'm sure Dr. Sperano did that. So he says KPQ is a Banach space relative to the norm we defined on the section of supervector spaces, and he says let tau n denote the topology on KPQ, where U belongs to it if and only if. So his Tn is the norm topology, all right? You might call it the Banach topology. It's the topology generated by open balls built from the norm. That's the topology that we want to use ultimately. Because that's the rich one that is Hausdorff and will allow us to do all kinds of really quirky stuff in the odd directions that'll, I'm hoping, will give us a paper that make people go, what are they doing and why are they doing it? Which is not, in some sense, the best way to write a paper. Like usually people want to find a problem and solve it. I just want to show the richness of our construction and like how much weird topology we can weave into the odd coordinates. So then he talks about here, there's a second topology, tau sub d. D is for DeWitt, where the set is open if and only if it's the inverse image under the body map of some open subset of Kp with its norm topology. All right, where B is the body mapping from KPQ into Kp. So let me talk about that a bit, because we haven't talked much about that. I don't think we talked about that at all yet. So KPQ, right, is x comma theta, right? such that, you know, x is an element of kc p-fold times theta is an element of ka p-fold times, right? So of course you could write it more. I mean, you can also write it like this, right? This is the other notation for it, like z upper m. Here's a really dumb notation. Oh, there's no p here. Duh. That might be a physicist kind of notation. Right? Use the letter of the indices to indicate the idea. But, all right. So what's the body map? So each z, if you will, each zm is equal to a sum, right? Over I of z upper m lower I a to I, right? And the body of any such supernumber, golly, yellers. My children are going to swimming practice every day this summer, starting at 8:30. Like, can you imagine getting in a pool at 8:30 this morning? Yeah, it's gotta be. It's crazy. Whew. Anyway.
I'm a little confused here in the second notation.
My bad.
So,
That was supposed to be an m,
in the other one.
and this is supposed to be 0. What's that?
In the second notation for k, pq.
Yeah.
So, the first m is a capital M. So
Yeah, I mean to put a capital M here, my bad.
And so, where m equal?
Yeah. I mean, you could use this kind of dumb notation if you wanted to, but I mean, we like to use this, I like the z notation. So we will soon talk about the tangent space to a supermanifold, right? And you could so it's the span over the supernumbers of partial zm at the point P. So it's nice if I want to talk about the supercoordinates as a whole, but sometimes I want to talk about the even-odd structure. Then I want to break the z's into like x's and thetas. So this big indice is useful. I mean, it's nice to have both notations, but it's kind of, well, I guess, okay, so anyway, is that, if in doubt, of course, we can always, and I think when the book, like, this is one of the things I must be much more careful about, is trying to get rid of this. And this is a book for math majors and physics majors. So since it's for math majors, like, I don't want to, I want if I'm going to do something with notation like that, it's got to be, like, clearly, it can't be just scattered here and there. And I'm mostly telling you that because I know that is in there. So as you're reading it, I want to make sure you understand, like, anyway. It's like the repeated index notation. You know, when an index is repeated, it's summed over. This is Einstein's repeated index notation. I don't use this in linear algebra, but if I did, it would save me all kinds of writing. Because every time I have a sum, I could just repeat an index, but it would just be very unhelpful when we're really trying to be careful about sums. So there's some of that here. Anyway, so the body map just picks off the 0th Grassmann component. Right, these are supernumbers. So there's infinitely many terms here. You're just throwing them all away. And so what he's saying is that the body map, I mean, so we can talk about the body map on KPQ, right? It's a mapping to, well, effectively it's a mapping to KP, where, and in here I really do mean, I guess for us it's CP. I guess for us it's CP. I mean, I don't know. I'll leave it like this for the moment. This is we should have made a decision about 20 years ago and just stuck with it, so I'm not still doing this. But anyway, the reason I say to this is if you think about, I mean, you can identify it with that, because if we think the body map I'm going to define, you know, if we have the body map of, you know, x1, and I'll just write it out this time. So you got px's, and you got how many thetas? Q thetas, right? It's just going to be defined to be the body of the first one, body of the second one, body of the pth one, body of the theta 1, body of the theta q, right? But think about it. The odd supervariable, right, takes its values, like all of these theta, you know, theta, let's say theta alpha takes values in, you know, I called it k sub a, or you could call it lambda 1, right? And so what does that mean? I mean, you have an odd number of Grassmann generators, right? And the expansions. So there is no zeroth component. They only have soul. There's no body. Which means that these are all zero, right? So this is sort of the naive, what I just wrote is the naive definition. So basically the definition is just to cut it off here, I think is essentially what he's saying, is you can meaningfully just define the body map from KPQ to KP, right? And what he's saying is that the DeWitt topology, right? So let's see here. U, a subset of KPQ, right, is open in the DeWitt topology. If and only if what? There exists V open in KP. And here we're talking about finite dimensional normed vector spaces. Like this is just regular metric finite dimensional open set, right? There's nothing, this is stuff you've talked about in other courses, really, right? Such that what? U is the inverse image of that open set. Another way to say this is the DeWitt topology makes, I guess it makes the body map continuous, right? I mean, is the body map continuous? Well, the inverse image of open sets is it's open. So I guess it's continuous. Now, so that's what makes a set open in the DeWitt topology. So let's see here. So this is the definition of so-called tau D, right? Okay, so let's think about something. For example, if you had 0, 1, right? Cartesian product with itself p-fold times. This is a subset of Kp, right? Is open, yeah? So what would the inverse image of this look like in the body? What would those kind of, superspace elements look like? You'd be talking about what, like x comma theta such that what? What conditions do you face? You're just stuck with the condition that, the body of x is an element of 0, 1, the p. In other words, basically it's the only condition you really face on the set is to make the, x m 0 to be 0 less than this, less than 1, right? Otherwise, for example, the x sub m sub I are, unrestricted, right? And of course, the theta j mu are unrestricted. Well, these are just range over all k a, right? And these are unrestricted for I not equal to the 0, like that's what an open set looks like in KPQ with respect to the DeWitt topology. It's very unstructured with respect to the Grassmann directions. In contrast, right, we could, let's see here, if we're using the norm, let's think about how could we define an open set in KPQ using the norm. Like, for example, if we look at tau n, for KPQ, we could look at the ball, for example, centered at the radius epsilon, right? Centered at, well, let's say radius 1 for the sake of specificity. Radius 1 centered at 0, right? So that would be, x comma theta in KPQ such that the norm of x comma theta is, well, minus 0, right? But that's just x theta is less than 1. And so, to be more explicit, we're talking about, man, there's a lot. There's a lot here. But the sum, let's say m equals 1 to p of the sum of im of x sub im, my bad. No, down here. X upper m, I'll put the im down here like this as well. Well, we don't need the etas. We're taking the norm, so this guy, that's the norm of this. And then plus the sum, let's say mu equals 1 to q. The sum over, let's say j mu of the absolute value of, theta upper mu, lower j mu, like that, all of that less than 1. Which means, obviously, these are not unrestricted. And even the Grassmann, the non-body parts of the commuting variable, are also restricted. And this is an open set. Now, what does this matter? All right, so for example, if you think about, the point down here in Kp, I don't know, could be P equal to, let's say, 1 and then zeros afterwards, okay? We'll just look at that as a point, just for the sake of specificity. All right. Then I can draw a picture above, like up here. All right. This is the inverse image of P. Up here in, KPQ is my picture up here. Essentially, if your open set in the DeWitt topology intersects any part of this, it has to have all of it. You can't have an open set in the DeWitt topology which separates. You can't separate these points in the DeWitt topology. On the other hand, I believe we could pick a point here and pick a point here, so to speak. Let me be more explicit just for the sake of discussion. So this could be like, oh, I don't know, 1 plus, eta 1, and this point up here could be, oh, I don't know, comma zeros. Let's just keep the thing simple, right? And this one could be 1 plus eta 1, eta 2. These both project down to that point under the body map, right? They both go to the point P under the body map. So if I'm using the DeWitt topology, I cannot find two open sets which contain this and that respectively and have disjoint union. They're disjoint. Can we find open sets in the norm topology which separate those points? I mean, I think I could use the ball. I mean, I don't know, I guess. I'm really not sure. I'm going to just trying something here. Maybe ball of radius a half. Centered at 1 plus a to 1. And the ball of radius 1/2 centered at 1 plus a to 1, a to 2, right? So this contains 1 plus a to 1, right? This contains 1 plus a to 1, a to 2. They're both open essentially by definition, right? Because the open balls generate the topology in the norm topology. And I want to say these are disjoint. I don't know though. How would you check? So here's the question. Is 1 plus a to 1 an element of the ball of radius 1/2 of 1 plus a to 1, a to 2, right? I mean, I need more than that. I need that the balls are disjoint, right? But this is a starting point. Like, if this isn't true, then I know I need to start again. How do we judge this, though? We look at the norm, and my bad. I'm supposed to be doing comma 0, comma 0, comma 0, you know? So, like, my bad. So, so we've got is 1 plus a to 1, comma 0, minus 1 plus a to 1, a to 2, comma 0. What's that equal to? It's the norm of what? A to 1 minus a to 1, a to 2, comma 0, which is 2. See, because the, I mean, it's literally equal to the norm of this Grassmann number, which we define to be the norm of 1 plus the absolute value of minus 1, which is 2. So, nah. Okay. So now what I need to do? So I should let Z be an element of, you know, be 1/2 of, you know, 1 plus a to 1, a to 2, comma 0, right? And I should look at what is the distance between Z minus, and I should let W, right, be an, well, no. I just need to look at, my bad. I just need to look at 1 plus a to 1, right? I'm trying to decide whether or not any point in here is in there. So it suffices to look at this. And so what do you got? Well, you've got the norm of, let's see here.
Could you use the triangle inequality?
Yeah, maybe something,
Because the norm of C would be less than 1.
oh, this is less than, okay, less than or equal to the norm of Z. But I mean, okay, I'm not disagreeing. You know, yeah, sure. But trying to decide if I want that to be less than 1/2. Excuse me, I need it to be greater than, I want to show it's greater than 1/2, right? So I think the triangle inequality, while true, maybe it's unhelpful here. Yeah. So, look, so z we can write more, I mean, we should take it, I mean, what is z? Z is in here, right? So that means that we've got, okay, so we should do this. We should do like, okay, so that's the norm of z, z minus, parentheses, 1 plus eta 1, eta 2, right? Plus what? 1 plus my bad. I'm sorry, this notation's playing havoc with me. So comma 0, right? Plus 1 plus eta 1, eta 2, comma 0, minus 1, comma 1 plus eta 1, comma 0. So what I did was I added 0 in the middle. I don't need parentheses here.
Okay.
Added 0. Now then, this is, what we got here? We got norm of z minus, I mean, this may not be helpful either, but I'm just trying something. Oops. Now this simplifies to what though? Ones cancel, right? So we got eta 1, eta 2, minus eta 1, right?
And the first one is less than 1/2. I mean, z minus 1 plus eta 1, eta 2, comma 0. Because c is an element of the open book.
So we want this to be, we want to make this greater than or equal to something, right? Because then we would have that z minus, we would have that z is not an element of the ball centered at 1 plus eta 1, right? So how does that inequality go? What's the... I mean, of course we know the triangle inequality, but what's the other one? If we have the norm of like, so we have norm of a plus b, right? Less than or equal to norm a plus norm b I'm thinking we can I always forget this stupid thing, but I think it's norm a minus b.
It's greater than,
Yeah. Absolute value, right, of norm b minus norm a. hope that's right. I always have trouble proving that, but so let's suppose it's, I mean, so it would be good to try to prove this from the triangle inequality, right? Independent of it being absolute. I mean, this is definitely true for absolute value. Is it true for norm? I think it is. So in view of this being, you know, you can think of this as being A and this being, you know, B or minus B, if you like, right? Then this is greater than the absolute value of the norm of Z minus, you know, 1 plus eta 1, eta 2, right? Oops, my bad. Minus the norm of you know, eta 1, eta 2 minus eta 1, 0, absolute value, right? Which would be equal to, well, oh, phooey. All right, so it's greater than or equal to this thing. You got to watch me with inequalities. I make mistakes. I can talk myself into things sometimes, so you got to be leery of me. This is 2. Let's see here. So the norm of, well, this is at most 1/2, and not even that, right? At most, almost 1/2, right? And the words fail me, right? Because it doesn't even get to 1/2. So that's almost 1/2. That's 2. So this is what? This is greater than 3/2, right? I mean, it can't be equal to 3/2 either, because this, you know, this can't be 1/2. At most, it could be like 0.499. So that would give you, so if this was 0, this would be 2. Wait a minute, no. Yeah, okay, if this was 0, this would be 2. Is 2 greater than 3/2? Yes. So that checks. But anyway, the larger point is this, so therefore what? Z minus 1 plus eta 1, 0, right? Is not less than 1/2. So therefore Z is not an element of the ball of radius 1/2 of 1 plus eta 1. Right. Which shows you that I have just separated those 2 points. So that's something you can't do in the duet topology, but we can do.